Hello everyone, today I'm going to talk about the paper Dynamic Time Warping Based Proximity Problems by Boris Aronov, Matthew J. Katz, and myself, Elad Zulami. So we'll start with an introduction, what is dynamic time warping. Next, we're going to share our results for different problems that we solve in the paper. Next, we're going to share two algorithms that solve distance oracle, and we'll finish with the experimental study and some open questions that we have left from the paper. So first, what is dynamic time warping? It's a similarity measure for curves. So here in the image, the red curve and the blue curve, we want to know how similar they are. So it's been used for speak recognition, signature matching, time series comparison, and more. And other known similarity measures are Frechet distance and Hausdorff distance. So to explain how dynamic time warping works, we're going to need to explain first what is an alignment. So an alignment between two curves P and Q, here in the image, the blue one and the red one, is a sequence of pairs such that each pair is an index from the first curve P and the second curve Q. And this sequence has to hold some conditions. And to explain those conditions, we're gonna need to imagine we have a frog for the P curve and the frog for the Q curve. And those frogs start from the first point of both curves and end in the last point of both curves. And in each turn, either the P frog advances to the next point, or the Q frog advances to the next point, or both of them advances to the next point. And you can see that there are many possible different alignments. Here, in the example, the alignment is the black lines that you can see here. And you can see that both frogs start from the first point. Next, both of them advances. Next, only the Q frog advances. Next, again, both of them advances. And next, only the P frog advances. And you can see they end on the last point of both curves. So the next term that we're going to need to explain is what is the cost of an alignment. So the cost of an alignment is just the sum of distances of all of the pairs in the alignment. So here it's just the sum of lengths of the black lines. Out of all possible alignments, we'll take the minimum cost of all possible alignments, and this will be the dynamic time warping distance. So this distance can be found with a dynamic programming algorithm within theta of M1 and M2, where M1 and M2 is the sizes of the curves. In our paper, we solved problems using a specific setting, where in this setting, every time we measure distance between two curves, one of the curves is just a segment. Here you can see the blue segment AB. And in this setting, to find an alignment between the blue curve and the red curve is just to find the prefix of size j and the suffix of size m minus j, where m is the size of the curve of the red curve. And the prefix will be matched to the first point A, and the suffix will be matched to the second point B. And this is an alignment. Okay, so the first result that we have is for the first problem that we solved is for distance oracle. So given a curve of C in RD, we want to construct a data structure that will answer queries such that each query is a segment, and we return the distance between the curve C and the segment S, and the segment query S. The first result is a data structure of size m log n, and it returns the distance within log to the power of 3m, and it returns actually a two approximation to the distance, and this two approximation is in L1. So what this means is in every alignment, the pairs of the points, the distance will be in L1 metric. And this is the first data structure that we found. And the second data structure is actually for exact queries, so not just an approximation, but here it's the metric is in L infinity, and you can see that the size of the data structure is much larger, and also the construction time. Both of the, and even though the query time is just log n. So the next problem that we solved is segment center. So here we have a set of curves of size n, such that each curve is maximum size m. This is also in RD, and we want to find a segment that minimizes the distance to the farthest curve to the segment. So here we found two different algorithms which yield different results. So depends on the size of n and m, will choose the suitable algorithm and will return the result. Here also the distance metric between every 2 points is L infinity. And the next problem that we solved is nearest neighbor. So here again, we have a set of curves. You can see here in the image, and we want to build a data structure that answers query segments. So for each segment query, we want to return the closest curve to this segment. So here maybe for the black segment, we'll return the purple segment, and maybe for the purple curve, sorry, and for the blue segment, we'll return maybe the red curve. So you can see that the query time is log n m, and that structure is quite large. Okay, so let's dive into the first problem, distance oracle. Again, here we have a curve, and we want to build a data structure for the curve that answers query segments. So the query segment will be maybe the blue one, the yellow one, and the purple. And this data structure answers what is the distance between the curve and the query segments. And we'll present two algorithms. Both of them will present in the one-dimensional case, but you can extend them to any dimension d. So let's start with the first algorithm. Again, we have a curve C and some segment query S. And we'll define first three functions, f, g, and h, discrete functions. And f will be the sum of distances of a prefix of size I. Fi will be sum of distances of the prefix of size I to the point P. And GI will be the sum of distances of the suffix of size m minus I to the second point, Q. And HI will be just the sum of Fi and GI. And you can see that F is an increasing function and G is a decreasing function, because every time we'll add will increase I, will add one more point to the sum, and when we'll increase I for G, we'll remove 1 point of the sum. And you can also see that HI is just the cost of the alignment, where the alignment is defined by the prefix of size I. Okay, so the first lemma is for two cases. The first case where F is above G. In this case, we will say that H1 is a true approximation to the dynamic time warping distance. And when G is above F, we'll say that Hm minus 1 is a true approximation. So we'll prove just the first case, and the second case is symmetric. So in the first case, we'll say that L is the index for which the dynamic time warping distance is HL. So 2 times the dynamic time warping is 2HL, and from the definition of H equals F plus G, so we'll get the following equality. And next, we'll just remove the G, and we get a small value. And since f is an increasing function, so f1 is less or equals to fl, and since f is above g in our case, then f1 is larger than g1, so we'll get the next inequality and we got the two approximation. And the more common case is where f intersects with g, and it's the more interesting one as well. So in this case, we'll look at the index before the intersection k and the index after the intersection k plus 1, and we'll say that the minimum of hk and hk plus 1 is a two approximation. So to prove this again, we'll say that hl is the index for which L is the index for which HL is the dynamic time warping, and we'll assume first that L is less or equals to K. So L is somewhere to the left of K, and okay, so we'll say that 2 times the dynamic time warping, again, by the definition of HL is 2HL, and next H, by the definition of H equals to F plus G, and again, we'll remove the F part, we'll get 2 times GL, and since L is smaller than K, and for K or smaller values, G is above F, so we'll get that GK is above FK, so we'll get the next inequality, and again, by the definition of H, we got the two approximation. And the second case where L is larger than K, it's symmetric. You just need to replace K with K plus 1 and G with F. Okay, so now that we have both of our lemmas, we're gonna need to divide two cases. So the first case where F is above G, will just return H1, and for the second case where G is above F, we'll return HM minus 1. And if we're on the third case where G and F intersect, then we'll find K with a binary search, and then we'll return the minimum between HK and HK plus 1. And this is the algorithm again for returning a two approximation in L1 metric. Again, the L1 metric is for every 2 points that we want to know the distance between them, it's in L1 metric. Okay, so the next algorithm, again, it's for exact queries, not just an approximation. And this time, for every 2 points that we measure the distance between them, it will be in L infinity. So the first thing we're going to need to define is taus. So taus is just a partition of the line into intervals. So here the curve is P1, next it's P2, it's a zigzag as you can see, but the taus are by the order of the points on the line. So the first tau is between minus infinity and the smallest point, and the last one is between the largest point and infinity, and all of the rest is just a partition that this curve of the line by the curve. And for each pair of 2 taus, so we'll show an example later for tau 2 and tau 4, we'll build a data structure that this data structure will answer the dynamic time warping distance between the curve and points where the first point lies within tau A and the second point lies within tau B. Again, the queries are segments, so we have 2 points, A and B, and the data structure will answer queries such that A is within tau A and B is within tau B. So now for every tau A, tau B, we'll build set of functions for every j between 1 and m minus 1. And this function, again, will define the cost of an alignment where where the prefix is of the size j, and the suffix is of the size m minus j. So here in the example, you can see tau a and tau b. And let's say that the prefix is of the size 3, so j equals 3. And this partition the points to 4 groups, as you can see in the 4 different colors. And those groups define the sum of the alignment. So here you can see that by the definition of tau a and tau b, we just got rid of the distance metric with the absolute value, and we, instead of this, we'll define this linear function, given the knowledge that we know that A lies here and B lies here. We can tell if we need to subtract the points, the points from the first point, or to subtract the point from the points from the first point, or the other way around. And so here in the example for j equals 3, we know if A lies here, we need to subtract P1 from A and P2 from A, and to subtract A from P3. And the same applies to P4 and P5 from the point P. As I said, this defines the cost of the alignment, and we can actually pre-compute Fj, so we can return Fjab in constant time. And now that we have this bivariate function, the graph of this function is actually a plane. So next, we're gonna define a rectangle tau a times tau b, and we'll show the image first, so it will be easier to explain. So we have the graph of the functions. So each graph is a plane. You can imagine that each line here is a plane, and we'll take the lower envelope of those planes. Okay, so the lower envelope of those planes actually represents the dynamic time warping distance between every 2 points within tau a, tau b in the rectangle R. So the lower envelope represents, because it's the minimum value of all of the functions for point AB in tau a, tau b, it represents the dynamic time warping distance between those points and the curve C. And now that we have this lower envelope, which is a piecewise linear function, all we need to do is, given A and B that lies within tau a, tau b, we'll need to find the function that is above AB. And this function will yield the dynamic time warping distance between AB and the curve C. Okay, so to do that, we'll pre-process the lower envelope for vertical ray shooting queries. So given a segment, we'll perform a query, a ray shooting query, and we'll get the function that will return the dynamic time warping distance. This can be done, the construction can be done in m log n time, and the queries can be answered in log n time. And this completes the description for just one pair of tau a, tau b. And since we have m squared pairs of tau a, tau b, then we'll get total size of m to the power of 3. Okay, so sorry, this concludes the description of the second algorithm. Again, this algorithm yields a quite large data structure, but the queries are pretty fast. It's in log n. Okay, so next, the experimental study. In the experimental study, we try to understand better the size, not the size, we try to understand better the data structure that we just talked about. To do that, we wrote a program that first generates a curve. You can see here the curve. And next, it generates a lot of random segments. So for each segment, we found the index j for which fjab is the dynamic time warping distance. So we found the best or the best alignment that yields the minimum cost of the minimum cost of the alignment. And for this index, we put the point AB on the map with the color J. So again, we found the minimum alignment. This alignment is defined by the size of the prefix J. And for this J, we put the point AB on the map with the color J. And this generated the following maps you can see here on the image for different curves. And if we can understand the size of those maps, the complexity of those maps, maybe we can reduce the size of the data structure that we just talked about. So we talked about the data structure of the size m to the power of 3. And maybe if we can understand the complexity of those maps, here you can see examples for curves of size 10. Maybe we can reduce this complexity of the data structure. So this is actually the first open question that we have from the paper. And the second open question is even more interesting. So can we extend the algorithms that we just showed to work with curves of size of m instead of just curves, instead of just segments? So that's it. Thank you.